Welcome to Control Systems N6. Today's presentation is going to be on block diagram algebra. This is a module that is quite interesting and very important for you to understand. The reason being that you will always get a question from this module in your exam. I need to say that the textbook that has been prescribed to you does not give you all the information that you need to be able to fully understand block diagrams. And so in this presentation, what I am going to do is take you through everything that you need to understand so that you will be able to tackle any question that you may get from this module. Let's begin. First, what is a block diagram? A block diagram is just a graphical representation of a control system. Generally in engineering, any system will have a graphical representation. And so when you're dealing with a control system more specifically, its graphical representation is what we refer to as a block diagram because it is made of blocks. And why is a block diagram useful? Okay, they are useful because they allow us to build a mathematical model of the control system that will help us establish a relationship between the input to the system and the corresponding output. So that is very, very important. Just by looking at a block diagram and understanding the operations that need to be made, it is very possible for you to come up with a function that will allow you to relate the input to the system to the corresponding output, okay? And so that function is what we refer to as the transfer function. The transfer function is a function that allows us to relate the input to a system to the corresponding output. And so what you're looking at here is a simple block diagram because you just have one block and you can see you have one arrow going in and you have the other arrow coming out. And so the arrow going in will of course represent the input and the arrow going out of that block is the output. Now, in control systems, we usually use the letter R to refer to inputs, and this R is a function of S because we are in the Laplace domain. And so R is used to refer to inputs, and C is used to refer to outputs, okay? In some cases, they may also use X and Y, but generally it's going to be R and S, especially in this module. Inputs, we use the letter R, and for outputs, we use the letter C. Okay, so both of them are functions of S because we are in the S domain or the Laplace domain. And so these two functions, the input and the output, are related through a transfer function. So what you see here is the transfer function that relates the input to the output. Okay, so this is the transfer function. GS is the transfer function in this case. And so the equation we use to relate the input to the output of a control system is simply this one. So basically, the output function divided by the input function is equal to the transfer function. Okay, in this case, this is the transfer function. And so let us now look at a real example of a control system, which is what you see here. As you can see, you do not just have one block as we had in this very simple example, but rather you have a number of blocks in the system, and you can see that you have so much going on here. And so, in order for you to be able to establish the relationship between the input to the system and the output of the system, what you need to do is to reduce this system that you see here into one block. So you need to find a block that can replace everything that is going on here, but that will still give the same output as this whole system. Okay, so when we are reducing it like that, basically what we're doing is replacing all of what is going on here with just one block like that, but this block must produce the same outcome as the entire system. Okay, and so when we do that, this is what we refer to as reduction. Okay, so we have reduced the system to just this one block, but this one block is a transfer function that will produce the same output for this input as the previous system that was on the screen before we reduced it to this one block. So essentially, this system that has been reduced is equivalent to the system that was there before with the many blocks. So they are similar, they are equivalent because they both produce the same results for the same input. Okay. However, this one here is easy to work with because we're just dealing with one block and one transfer function. Okay. And that is very, very important to understand. And so for this module, this is exactly what we are going to be doing. We are going to be reducing very complicated control systems into a simple control system that is just made of an input, a transfer function, and then an output. Okay, so that is basically the exercise that we will do in this module. And so again, I will remind you that the relationship that relates the output to the input is this one. Basically, the output divided by the input is equal to the transfer function. And again, this output C here is a function of S. Okay, generally in your block diagrams, they will not write the S in brackets. They will just write C as you see they did here. But what is meant by that is that this C is actually a function of S. Same thing with R that you see here, it is a function of S. And so the ratio of the output to the input is actually equal to the transfer function of the system. So what is the transfer function of the system? The transfer function of the system is pretty much the gain of the one block that will replace all the blocks in the system but still produce the same outcome as the system. Okay, so very, very important to understand that. Now, before we begin to analyze control systems and block diagrams, we need to understand the two types of junctions that we have when we're dealing with block diagrams. So the first one is what we call a summing point. It is also called a summing junction, okay? And what is a summing point? It's represented by a circle like that in your block diagram. And this is basically a point, a place in the block diagram where signals can be added, okay? Or maybe you can add one signal and subtract another, okay? But this circle here, whenever you see that in your block diagram, it is a summing point. That is what it represents. So this is a place where signals can be added or subtracted and so on and so forth. So let's say, for instance, you have this signal here, R1, which is being added to the system. So the way you will show it, you will show R1, you will show an arrow going to the summing point, and because it is being added next to the arrow, you will put a plus sign. And you may have also another signal being added there, and again you can see we have a plus sign. So the output here will therefore be the sum of the two, because these two signals are being added by means of the summing point. Therefore, the signal that you will have coming out here will be the sum of the two. It will be R1 plus R2. And here I just need to point out that in some cases you may find that this here is drawn like that, and you can see they did not put the signs, okay? And in some cases, in some block diagrams, you will see that when it is positive, okay, they just don't put the sign. They will only put the sign if it is negative. So if you see a block diagram where you see signals coming in to a summing point and you do not see any sign next to the arrows, just assume that it is positive, because in some conventions, when the signal that is being added is positive, they do not write any signs. Okay, so they find it pointless to put the sign. They will only put the sign if the signal coming in was actually a negative addition. Okay, so let us look at another example of a summing point. Again, here you have a signal R1 that is being added, but then at the bottom you have a signal R2 which is coming in as a negative. Okay, and so in this case, the output signal that you will have will be therefore R1 minus R2, because here you have a negative. And so if we use this convention or this way of drawing block diagrams, then in this case it will look like that. As you can see, again, where the sign is positive, we put nothing. We only signal when the sign is negative. Okay, so if you see a representation like that in your block diagram, you don't need to begin to wonder what is the sign of R1. Okay, if you see no signs, it means it's positive, but they will always let you know if the sign is negative. But in some other block diagrams, they will let you know when it's positive, so you will have a plus and you will also have a minus. Okay, but in other representations, when it is a plus, they just don't put anything. They only signal when it is a negative. Okay, so I needed to show you this so that you do not get lost when you are dealing with block diagrams. And so let us look now at this. Again, you can see we have three summing points, and you can see that these signals are added at the summing point. So you have one signal here, one signal there, one signal there. Okay, and so what I want to show you first is that even if we swipe the order of the way the signals are going into the summing points, the outcome is still the same. So basically what you have here is the same thing as what you have here. And you can see here we now have R3 going in to this summing point, and then we have R2 coming into this summing point. And in the previous picture, it was R2 first and then R3. But because these are summing points, whether we do it this way or that way, it is the same result that is going to be produced. Okay, if you say A plus B, that is equal to B plus A. It doesn't matter which you do first. So with summing points, you can swipe them like that. That will not affect the outcome. And also, it is important to not always have unnecessary numbers of summing points. In this case, for instance, you could add the three signals on just one summing point. So it could have been like that. And so what you see here is equivalent to this, and it is also equivalent to that. Okay, so it's very important for you to understand that. And so having said that, this is what you need to know about summing points. The second type of junctions we're going to talk about is takeoff points. And takeoff points are represented by a big dot like that. And so simply, what is a takeoff point? It's a place where the signal branches out into many directions. That is basically what a takeoff point is. So let's say the signal that you had here coming into the takeoff point was R, and now we have a takeoff point allowing the signal to now branch out in three different directions. So each of these will also have the same signal R. Okay, so this is what a takeoff point is. It's simply a junction where the signal is allowed to branch out in different directions. Okay, so that's what a takeoff point is.